Okay, so it seems like this stream's working. Right, it's about 7 o'clock, so just give me 1 second and then I'll get started on this review. I'm just gonna grab some water. Right, okay, so let's go ahead and get started. So yeah, hi, I'm Jerry, I tutor signals here, and I'll be going over the material for your last exam in this course. So let's see, let's go ahead and get started. Also, I usually sit in tutoring room 1 if you're part of the IEEE Discord. I usually sit there for people to ask me questions in real time. I tend to be better about responding to those than I am about looking in the chat or saying the tutoring chats for in the Discord. So yeah, I would really appreciate if you all had questions. You could if you could speak up because that'd be the best way to reach me. But anyway, so I'm just going to go ahead and get started. So the theme of this session today is discrete time processing. We're going to be talking about how do we process discrete signals, mostly through the sampling theorem and the Z-transform. We're going to talk a little bit about the continuous domain with Laplace transforms and differential equations, but not really too much because that's not really the focus in most sections of this course. As far as I know, that Fumagalli is the only one that really puts a little more focus at the end on continuous time signals. But here we go. Let's talk about discrete signals. So what's a discrete signal? The most important quality is that we can count the number of samples. So we can just we can enumerate all of the little spikes that occur in our signal if it's represented in this way, where it's just a series of values like this. We can also represent it like in a bit more of a compact form by just writing out as a list. Sometimes you'll see it's denoted with an arrow where the 0 point is. So if we look at this signal that's defined by a function, we can also have that too, this cosine. The value at 0 is 1, as indicated by the arrow. So let's go ahead and get started on sampling. So now that that's out of the way. So a big problem is, well, how do we get discrete signals? Let's see. So one way is that they could just be given to you. They usually from like something with a clock. So most computers, usually if they're represented in a programming language, they're going to be an array. Sometimes you might get them as a list. They can also be given to you, so you can also get discrete time signals naturally. So we might ask someone to rate something from 1 to 5, or you want to get a gathering of like or you want to like count quantities of something at regular intervals, like the number of leaves. That would also be a discrete signal, because we can only have values that belong to, like, say, like 1 to like 27, or integers in that range. But the more important one that we are going to talk about is sampling. So we can get a discrete time signal from a continuous time signal. And this is done by evaluating that continuous time signal over a set of integers. So, or just a discrete set of points. And this takes us from the continuous time to the discrete time. And we can also get back under certain conditions. But the main idea is that we just need to get a bunch of points from just something that looks fairly continuous, like kind of wiggly. And so in this course, we are mainly concerned with what's called fixed rate sampling. So this is where we usually put the distance between each sample in time is going to be the same. So it's going to have like 0.1, 0.1, 0.1 difference, 0.1 difference, 0.1 difference between each samples. And yeah, so we can represent this mathematically by just putting in our discrete variable m, which is just a variable that belongs to integers. We put that in, and then we multiply that by our sampling period, our rate. And these two multiplied will give us a set of points described by our continuous time sample, or our continuous time signal. So we can also represent it as this sum of delta functions. So if we have so let me draw a picture because I like pictures. We love pictures. But yeah, if we have a continuous time signal, then so let's say that's our continuous time signal, then we can get samples of it by let's go ahead and just, well, I'm going to draw a bunch of arrows. And those are just going to represent a bunch of delta functions. So drawing in preview is really hard. So I think that you get the idea there. But let's see. Okay, so I mentioned that we can actually get back from this discrete time representation to a continuous time signal. We can go back under one condition. We need the Nyquist criterion to be satisfied. The sampling rate, the sampling frequency needs to be twice, it needs to be more than twice the maximum frequency. Yeah, as I show right there. And I'd like to give an idea about why exactly we use this inequality here in particular, just because I think that the real meat of this theorem is actually understanding what it means in the spectral domain to be doing sampling. So let's see. Okay, that didn't work. Okay, so yeah, here's the idea. Let's remember the convolution theorem. If we take the Fourier transform of something in the time domain of a multiplication, we can get the convolution in the frequency domain. And also vice versa. It works where if we convolve in the time domain, we can get multiplication in the frequency domain. We also remember that the Fourier transform of just a series of delta functions, so the sampling function, is also going to give us a series of deltas in the frequency domain. So, and we also know that if we convolve a signal with the Dirac delta, particularly one that's shifted over, then we'll also get a copy of the original. We'll get the original signal, but shifted, but the same amount as that delta function. So so represented graphically is if we let's see, draw. Okay, so let's see. Let's say we had a Dirac delta right here. Well, that should be an arrow that's upward. So if we had a delta function, let's say a, then if we convolve it with x, which is going to just be a box, because I love boxes. So if we convolve these two, we get original signal. That's convolution. We get. I wish I wouldn't do that. But we get these two. So we get a box that shifted over. That's the idea. Okay, and if we get that, then we get a bunch of copies in the frequency domain. So remember that we're convolving that series of delta functions in the frequency domain by our original spectrum. Yeah, this x of a. So if we do that, we get a bunch of copies in the frequency domain, and we can see this in the following figure. So look at this. Look at this. So if we can see a bunch of samplings of the same signal, this triangle function. So if we are sampling that signal, then we'll get a bunch of copies. But notice that the distance between these copies depends on something. This depends on our sampling frequency. You'll notice that the center point of each one of them corresponds to a multiple of our sampling frequency. So if we have a larger sampling frequency, then we're actually going to get more space in between here. But if we have a smaller sampling frequency, we're going to get them close together so that there's not a lot of space right there. There's no space right there. And if we have it too low, then we might actually get them to be overlapping right here. Yeah, this is called undersampling, oversampling, and I don't like the term perfect sampling, but yeah, hey. So we notice that there's an inverse relation between the sampling frequency. So the fs, so sampling frequency, why can't it just not draw arrows? So this is proportional to like the distance. That should be a proportional sign. I'm just gonna try to reduce my writing. But anyway, so higher sampling rate, more distance in the spectrum. Great. And this brings us to our formal statement of the sampling theorem. So if we have like just some band-limited signal, it's in the continuous time domain, then we can completely reconstruct it from its samples by making sure that the sampling frequency is greater than twice the maximum frequency. Yeah, like just if I wasn't clear. Oh, here I am drawing again. Okay, just if I wasn't clear, the maximum frequency of a band-limited signal would exist right here. This would be our omega m, or f of n, whichever one we're working with, whichever variable name we want to be working with. So that's that signal. And we can actually recover these copies. We can recover one of these copies by just applying an ideal low-pass filter. So a box, basically. If we were to multiply everything outside of one of these periods, then all of these would go away. All of those would go away, and we'd be left with our original signal, the triangle. But this is only possible. We can only get our original triangle back if there's space. If we can even do it here, if we draw our filter very carefully at this box. We can't do it here because there's overlap. It's going to not be exactly the triangle that we originally had. It's going to look more like a trapezoid, not parabola. Okay. But yeah, so this sampling frequency is pretty important because it lets us get back what we originally put in. We can invert this sampling, and we can go from analog domains to digital domains and vice versa. So we can process an analog signal with a computer, and we could have that computer spit back out that original continuous time signal. So it really doesn't matter which one we're working in. And yeah, so this last part just says that the cutoff frequency of our filter needs to be in between these two. So it's like, if this is f minus, so this distance here would be the maximum frequency. Yeah, since both of these are, this one is omega s plus the maximum, this one's omega s minus the maximum. So we need to have twice the sampling frequency in order to make sure there's enough space that we can put a filter in this white space. So now that we've talked a little bit about sampling, we're going to start talking about the Z-transform. And this is the mechanism that allows us to describe a lot of input-output relations in our discrete domains. So this is how we describe systems. These are the things that you'll actually be making. So I'd like to take a moment to actually ask a question. Why do we use the Z transform? Didn't we actually say during the Fourier analysis unit that the spectrum is the most important quality? That's what actually is how we can tell what our system's doing. That's the one that we actually see show up in real life. And yes, that's true. That's still true. The spectrum is usually what we're concerned with, but also the Z domain is what we usually have control over. So we don't have actual control over the values that go in our spectrum, usually. We have indirect control via what we call the zeros and poles of our transfer function. So the zeros and poles of our Z transform. So we need to make sure that we can have control. If we have controls of the zeros and poles, which is usually a weaker condition than having direct control of the values in our spectrum. So even if we can't shape like just a function in whatever application that we're working with, we can usually define it by the zeros and poles. Say like just a bunch of them. This might correspond to the spectrum up here, and vice versa. But like, so a few examples of where we might have control of the zeros and poles, but not necessarily of the spectrum, is so one that's relevant to us here as engineers is, as electrical engineers, we're concerned about AC circuit design. So the complex impedances that are defined by our inductors, capacitors, resistors, etc. So those are what we would consider the poles in our AC circuit. That is what we consider the poles. And if we want to design, say, an analog filter, then we would have to adjust our poles and zeros accordingly in order to construct the right spectrum. And we also see this in input-output relations defined in programs. So for digital filters, so like if we wanted to filter a signal digitally in a computer, we would have to define the input-output relation, which is mostly controlled by the poles. And we also have an example from mechanical engineering. If we have like a bunch of springs and masses, we can also represent those as poles for anyone that's interested in that type of thing. But it is mostly, I just wanted to say that, just to say that this is an important topic for all fields of engineering. It's kind of a universal model, this LTI system theory of, well, how can we put in something and then get back something that's more useful? That's kind of the idea of talking about these things. And as I hinted at before with filters, any input-output relation can be analyzed as a system. So anytime we're trying to put something in to an LTI system and we get something out, anytime that happens, then we can analyze it as a system here. So that's kind of the idea of doing the Z-transform business. It allows us to translate real-world problems into something that's easy to understand, or easier at least, something that we can work with. So now enough talk on that. Let's actually define the Z-transform. So the Z-transform is so the more general object that we would encounter in mathematics is called the Laurent series. It's basically like just a Taylor series. It's a Maclaurin series, but the one that we're interested in is that one where Z is centered to 0. So this is the series centered at the origin. Yeah, this summation right here. This is how we'd calculate a lot of our Z-transforms if we didn't have a table like you might have had in your homework. So this doesn't come, so the Z-transform itself isn't useful without its region of convergence. The region of convergence is just the set of points in the plane where that sum will converge. So it's usually going to look something like a ring. So it's either the exterior or the interior of our of some circle, and that's usually what we're concerned with. So, and both of these things are important together because both of these things will allow us to reconstruct some signal. So this means that there can be more than one different signal. Say, like, there can be more than one signal, x1 and x2, that will have the same z-transform, but they'll have different ROCs. That's why it's important to specify both if we're working in the z-domain. So before we talk more about the z-transform and actually getting them, we need to talk about causality. So we need to put our signals into different groups so that we can start talking about the region of convergence more thoroughly. So remember that a signal or a system, it's a causal signal if we have, a system is causal if we have the impulse response, it only works on the right side. It only exists there. So if we have like a signal defined here, maybe I should draw them up. No, that's even harder. Okay. Yeah, so if we have a signal here, this one would be a causal signal because there's nothing over here on the left side. That's 0. This is 0 all the way across. It would be equivalent to say that if we were to multiply our signal by the unit step function, as I write out there, then it would be the same signal. Now, a related idea is the idea of anti-causality. So if we have a impulse response that only exists on the left side, so an anti-causal signal would look something like this, where all its samples exist here and not over here, not there. And this would be equivalent to saying that if we multiply it by a shifted version of, so like a flipped and shifted step function, like this, yeah, it wouldn't have a value at 0, so it would be 0 at the origin, but it would be 1 for everything less than that. So that's our shifted unit step. That would be, if we multiply our original signal by that, we would get the same signal. That's what we call an anti-causal signal. And just something in between is something called a non-causal signal. That's where the impulse response exists on the left and the right side. So if we have, oh no, not like that. So if we have like, okay, so it's highlighted now. Okay, so if we have like that, then we'll have samples on either side. It doesn't matter. This would be a non-causal signal since there exists samples on the left and the right. Okay, so those are the types of signals that we're worried about. And now let's finally get to the region of convergence. Oh yeah, one last definition. So we're concerned about rational polynomial, or we're concerned about rational functions. So our z-transform is rational if it exists in this form, where a and b are both polynomials. So to get that out of the way, now that we have all that out of the way, we can finally actually tell you what your region of convergence is going to be. So if we have a causal signal, so if we look at our signal and we know it's causal, then the region of convergence of the region of convergence of the z-transform of that causal signal is going to be outside of some circle. It's going to be on the exterior. And the radius of this circle is going to be the maximum value, the maximum magnitude of our largest pole. Yeah, so the magnitude of our largest pole that's supposed to be an x. So like if you're given a zero pole diagram which has a bunch of x's and o's on it, then if you want the causal signal, then you'll take the region of convergence that is outside of your largest pole, so the largest x, and that'll identify a signal uniquely. And now we have anti-causal signals is going to be similar, but the opposite. So if we have our smallest pole now, the region of convergence is only really determined by its poles. We don't really care about the zeros. So if we have our smallest x here, it's going to be the inside of that circle. And so the magnitude of your smallest pole, the inside of that circle, is going to define an anti-causal signal. And non-causal signals will be something in between. It is going to have two different boundaries. So if all of these circles should be centered at the origin, by the way. Let me just draw that right. So a non-causal signal is going to have something in between the anti-causal and causal ROCs. So it's going to be in between two circles. It's going to be outside of one, which is smaller, outside of a circle defined by a smaller pole. It's going to be outside of that, and then inside of the region defined by the next largest pole. The ROC cannot contain any poles in it. That's the whole point of talking about these circles. There's going to be no poles within this shaded region. Yeah, just to really emphasize that. But yeah, you'll get this donut if you have a non-causal signal, or if you want a non-causal signal. And so if you have like a bunch of poles, then you'll have like a bunch of different non-causal signals that you can extract from a certain zero pole plot. And in order to specify further, you'll want to have other criterion that I'm not going to really talk about further here, but we can identify them uniquely. So now we're going to get to inverting the z-transform. So how do we get from the transform signal, and how do we get back to our original time domain discrete signal? How do we get that? So if we were to actually look at the formal definition, this is defined by something called a contouring integral. So it's like this. If you've ever seen it before, it's going to look something like that, and then it's going to have something inside there. But for the sake of this course, that's out of scope. Great, no integrals. So how do we actually go back? Then we'll use something called partial fraction decomposition. So we'll take our zeros and poles, we'll break them up, and then use a table to reconstruct our signal accordingly. And this works for most of the signals that we're interested in. So this is done by something called the Hebicide Coverup method. So yeah, we're going to cover up a pole, and then we can evaluate everything at that covered up pole, and then get a coefficient. And when we keep doing that for each pole, and then we get a series of fractions of linear terms in the denominator. And we can do this anytime we can factor a rational polynomial into its zeros and poles. Anytime that happens, then we can usually use this. Yeah, this works mainly for first order poles, and I'll probably do an example where we have a pole that's repeated, but we can always separate them into n and m poles, same as the order as of our polynomials b and a. So if we have so if we have a, well, that should not be a arrow, but if we have a, and it has like an x to the 5th term, then there would be 5 different roots of that. So there would be 5 different zeros. But if this was b, where it's in the denominator, and we had an x to the 5th, then we would have 5 different poles. So we would have 5 different terms here. The zeros don't really matter in this process for the most part, except for when you're evaluating to get these coefficients. And I'll show you more concretely what this means in our examples after this slides are done. That should be pretty soon. So, right, so I mentioned that we need to use a table to look up all of these common transforms. Yeah, this is how we'll use, this is how we are going to invert the Z transform for the sake of this course. So we just take, so if we have a decomposition into partial fractions, the linear terms like we saw, then notice that they kind of look something like these. Yeah, remember this series, all of these need to stop pressing the escape button. But yeah, all of these back here. So all of these linear terms in the denominator, all of those kind of look like these causal signals right here. We can also get, so these would be the transforms you would use if you have a causal ROC. So remember that a causal ROC is the one where it's outside of a circle. And if we have a non-causal signal, so an anti-causal signal, then we're going to use the one that's right here. Yeah, so if we want an anti-causal signal defined by an ROC that's the inside of a circle, then what we would do is we would use this one. And if we want to get something times a cosine, these are kind of useful if you have second order poles. If you have second order polynomials in your denominator, you can usually factor it into this form and get an answer outright without doing partial fractions. But honestly, I prefer to just break it up anyway. That's usually the foolproof method for a lot of problems. So let's see. So this in conjunction, so that table in conjunction with all of the properties that we learned in the course of the Z transform is going to be what allows us to go easily from the time domain to the frequency domain. The frequency domain, the Z domain. So yeah, we have a lot of the same ones that we had from the Fourier transform. Yeah, so linearity, time invariant, time shifting, scaling, reversal. All of those are very similar to that of the Fourier transform. So this is the one that allows us to get back just a series of functions in a series of signals from our partial fraction decompositions. So we can just multiply whatever this Z transform is times our constant, and then we'll get back what we want. And then if we apply a time shift in the time domain, this will correspond to a shift in frequency. Yeah, but we have to multiply by this like linear phase term, this Z to the minus k. Notice that this is very similar to the Fourier transform properties, where if we shift in the time domain, then we'll get like an e to the j theta. So we'll get that. So minus j theta times like our x. And that's just what oh, that should not be a circle, that's an omega. So this is the property as it looked like in the Fourier domain. Now we're just replacing our e, this e to the minus j theta, by just a z. Yeah. So that's time shifting. But if we So now scaling is a little bit different from the frequency domain, just because we have this a to the n term. So if we multiply it by a steadily increasing value, so this a to the n, this will either get smaller or larger as n increases. Then this corresponds to multiplying our variable by its reciprocal. So this also affects the ROC. And the way that you would prove this is you go back to the original definition of the Z transform. So you just plug in our scaled signal by that exponential term, and then you'll get that naturally. It will come out where you have to divide Z by A. And then we also get time reversal. So if we reverse in time, we just make sure that x, z, we just plug in z to the negative 1. We just flip z. Conjugation, you get conjugation in the z domain. And there's a lot of these others. The ones that are more important here is the differentiation. So if we multiply a signal by the variable, the index variable n, then we have to take the derivative of whatever our z transform is. So yeah, the integral, if we were multiplying by n here, we would start to integrate in the time domain. Yeah, so we differentiate in the frequency domain and then multiply it by a negative z. And this will also affect the ROC of our signal. And the last thing that's important is convolution. So we get a similar convolution theorem as I already kind of talked about as in the frequency domain. So if you multiply two signals, so if you convolve two signals in the time domain, then you get a multiplication in the frequency domain. So that's the convolution theorem, but just for z. And this gives us an ROC that's going to be smaller than R1 and R2 in general. So, as I talked about a bit earlier, I'm just going to go into a few more details about the Z transform, and we're going to go into solving problems pretty soon after. Because I think that most of these things, I've represented a lot of these things symbolically, but it'll make more sense if we start to just put numbers to things. Yeah, so if we control the spectrum with our poles and zeros, yeah, we can do that. And this is because the Fourier transform is actually just the Z transform, but we're evaluating our Z transform at the unit circle. It's just we're taking the Z transform and then we're plugging in a certain value of Z. So notice that the unit circle can be parameterized by this e to the j omega, where omega is just a real number. So if we take values along this unit circle, yet this is parameterized by our complex exponential in the z domain. And remember Euler's formula, where if we plug in if we plug in pi, then we get a value that's over here. If we plug in 0, then we get this value right here. If we plug in pi over 2, then we get an I term. And if we do 3 over 2, or negative pi over 2, then we'll get that negative, that other corresponding value. So yeah, this was kind of something that blew my mind the first time I saw it, but I think that it's kind of enlightening for telling you why that we use the Z transform. Why are we talking about it at all? This is what allows us to translate real-world problems into something that is more tractable for us. This is how we can manipulate real-world problems into a model that is more well-studied. And just as a final note, most of these results are going to have a corresponding continuous domain result via the Laplace transform. So if we're working in continuous time, then we'll use the Laplace transform. If we're working in the discrete time, discrete time, then this will give us, so then we want to use the Z transform. So I'm just going to quickly flash the results for the Laplace transform because that's not really the focus of this exam for the most part. And so here we go. It looks a little bit different, but at its core it's pretty similar. So if we have a constant, then we're going to divide by s. If we multiply by t, we're going to keep dividing by s. And you can go ahead and look at these. We should be familiar with these from differential equations, because that's the course of studies, these continuous time problems in more detail. But yeah, if, just as a reminder, here's all the same properties basically. It's very similar. I'll go over modulation because this is something that applies also in the Z domain to a certain extent. I'll go over those in my examples. So that's what I have for the theory, I guess. So basically that's all of the rules that you need to remember for your exam. I think that now is a good time to start really just putting some numbers to these equations and trying to understand how they work. Let's see. If there's anyone watching, if you have any questions, be sure to join me in tutoring room 1 so you can kind of ask, because I'm pretty bad at looking at that chat in the YouTube page or in the tutoring channel. So yeah, if you have any questions, let me know. So let's see. Let's go ahead and just start inverting a few Z transforms. So let's go ahead and just get that out of the way so we can get the mechanics down of the cover-up method. So let's define, that's pretty big. So let's say that this is our Z transform. So X is Z. So this is the Z transform of subsignal X. And we want to get the Z transform of X squared minus like 4. So how would we tackle this? So whenever you can, be sure to break up polynomials that are of higher order into their zero pole form. This will save you a lot of headaches. So if we factor this, then we get x minus 2 and x plus 2. So these two are equivalent. And now we can break it up into partial fractions. So I'm going to just write that form that we saw earlier, and we can solve for the coefficients later. X minus 2 plus b over x plus 2. So now what are a and b? So now let's just, so we remember that this is x is e times x minus 2, because we have to cover up the pole that corresponds to our coefficient a. We cross it out. So I'm just going to go ahead and write that out. So it's x minus 2 over x minus 2 times x plus 2. And so these will cancel, and we're left with 1 over x plus 2. And we evaluate this at wherever our pole is located. So x is equal to 2. So, oh shoot, I've been writing x, but this should be in z. Just make note of that in your head. So let me keep on going with x. I'll be sure to change that in a second. But yeah, so if we evaluate, then we get x over 2 plus 1 over 2 plus 2, and that gives us 4. So A is, so this one is going to be 1 over 4. And so B is going to be very similar. So we get xc times x plus 2, because we have to cover up the pole that corresponds to B. So we multiply it by that term, and then we get 1 over x minus 2, evaluated at x equals to minus 2, and then we get negative 1/4. So that's what we get right here. Minus. So that's B. Minus. So now at this point we can start to invert our Z transform. We can go from this back to the time domain signal. So I'm just going to go ahead and rewrite these x's as z. So z, z. So, and I'm going to copy and paste this one. Copy. Okay, so how do we do that? How do we use our table? Now that we have our partial fraction decomposition. So we're taking the inverse Z transform of this. That's what we're doing. All we were doing earlier is just rewriting our original Z transform into a form that we can work with. So remember linearity, we can break this up. So this is 1/4 times the inverse Z transform of 1 over Z minus 2 plus, so no, wait, minus 1/4. Linearity, I'm just applying linearity here. 1 over Z plus 2. And then we get our time domain signal as 1/4 Z minus 1. So remember that our Z domain signals are often defined, so our table values are defined in terms of Z inverse. So let me just go ahead and multiply by 1 on both of these. So what I mean is I'm going to multiply whatever's inside our Z transform. So we're going to multiply that by Z minus 1 and Z minus 2 times Z minus 1. So we're multiplying by 1. This whole thing is 1. Then this will come out to, let me just write it over here. So this is going to come out to Z minus 1 over 1 minus 2 Z inverse. So we get, so let me just copy and paste that in. So that, and notice that, let me go back to the table real quick. Let me erase so that in the middle. So let's go ahead and look at the table, because this looks a little bit different than that table entry for our causal exponential. That's essentially what this looks like, because we get this 1 minus 2 to the Z invert. We get that in the denominator, but we have this Z to the minus 1 up top. But if we remember the properties of the Z transform, this corresponds to, let me go ahead, let me pull that up. So we get, let me show you all the table. So if we multiply, if we have some Z to the minus K in our Z transform that's weird, then this will actually probably correspond to a time shift in our time domain signal. Then that's exactly what we have here, where K is minus 1. K is 1. So we get, so just going back to the table, we're going to, so going back to the table, where was the table at? It was before. So we got 1 over 1 minus a to the Z inverse. And now let's go back. and then let's plug those in, because we're going to get something similar for this one too. So this is equal to 1/4 times 2 n times u of n. And then we need to time shift it. So -1, -1. And that's it. That's this one. But we also have this other one. And we actually get something very similar. 1/1/4 minus 2. So we do the same process of multiplying by 1. And then we get n minus 1. U n minus 1. So we get a sum of two exponentials from this Z transform. And those are the types of signals that we're going to be concerned about for the most part. And let's see, so that's how you would do that. Just real quick, for a single order, for two single order poles. Yeah, so this is notice that there's no exponent here. That would be a second order pole. So, but we just have two of each pole. We just have one of each pole. There's no multiples, no higher multiplicities. So how about I show y'all an example of that exactly. So let's go ahead and invert this Z transform. So we got xz is 1 over z minus, let's see, 4 again. No, let's go 2. So if we had two of the same pole, what would happen? What happens here? So we can still break it up into partial fractions, but we'll need to do something a little bit different. So we multiply by, so we got a term, which is what we got on the bottom. Great. Both of our poles. We have two poles in the bottom of this one, and then we'll get a second one for the same pole where it's just a lower multiplicity. So notice that if we have a squared term, then we get two partial fractions. If I had like a 3, if we had, so let's say this one was 3, then we would have a plus c term, and then we get, so this one would be 3, 2, and then we get z minus 2. But let's go ahead and continue with the times 2 case. So we get those two. Now let's go ahead and evaluate for A and B. So now A, we can actually do the cover-up method again. So if we multiply xz times our highest multiplicity, so z minus 2 squared. So if we multiply that, and then we take it at is equal to, c is equal to 2. So let me go ahead and write this out explicitly so it's clear. So we get, so xz was 1 over z minus 2 squared, all squared. So what do we get here? Z minus 2 squared over z minus 2 squared. But great, all of these cancel. Okay, so we're left with 1, regardless of what we evaluate at. So A is 1. That's great. But now we get the problem of, what do we do for B? Let me write that in red, because I was writing those in red. So what do we get for B? So this is a bit different, because we can't multiply by this pole and then get back a valid, we can't get back a valid answer. Like if we were multiply, so let's go ahead and try the same method but with B. So this is one thing that I tried on an exam one time and it didn't go over well. So if we multiply by just a single order z minus 2, this is the wrong way. This is wrong. Wrong way. Yay. So we get 1 over z minus 2 squared, because that was xz, and then we multiply it by z minus 2. So this knocks down the multiplicity down, so one of them cancels out, and we're left with 1 over z minus 2. And if we evaluate this at z is equal to 2, notice that this will come out to infinity, because we'll get 0 over 0. If we plug in 2 here, then we'll get 2 minus 2, which is 0. We'll get 0 over 1, or 1 over 0, which is infinity. So that's not a valid answer. So we're going to have to just try out a different method. Now thankfully, since we only have one coefficient here, since we only have one thing that's left, we can go ahead and just multiply. We can just plug in some random number, and then we'll get our coefficient. No problem. So let's go ahead and do that. Let me just erase that. So that's the wrong way. Don't do that. But if we have, okay, so xz, so z minus 2 squared, so that was xz, and this one is equal to 1 over z minus 2 squared plus b over z minus 2. So how do we get b? We plug in just some random number. Let me just choose z is equal to, say, 0. 0. We just got to make sure it's not in the set of poles. That's it. So let me plug in z equals to 0. So we get negative 2 squared, which is 1 over 4. So let me write that, 1 over 4. And that's 1 over negative 2 squared again, so we get 4, plus b over z minus 2, so 0 minus 2, so minus 2. And now we can just solve for b. So we get 0 is equal to b over minus 2, so b is 0. So yeah, we did this partial fraction decomposition, and we actually get where this one is going to be 0. So this is actually the one that's all we need to do. We already had the original partial fraction decomposition in our Z transform. Right. So that's the idea there. And so this one is going to come. So this is going to come out to. Let's go ahead and try and invert this. Let's see what we get. So let me go ahead and make a new page. Let me just copy and paste. So we get XZ. Just copy, paste. And if we get that, then we get, oh wait, the parentheses outside. Okay, so we got that. Let's invert it. Let's get x of n is equal to z inverse of 1 over z minus 2 times 1 over z minus 2. Let's go ahead and write that. And remember, if we multiply a signal in the time domain, so this is a convolution property. So if we multiply in the frequency domain, then this comes out to a convolution in our time domain. So let's take, so we get z minus 2 convolved with the z transform, inverse z transform of 1 over z minus 2. And we get our causal exponential again, so that's going to be a pretty common thing. Yeah, so we get so 2. Yeah, 2 to the n minus 1, u n minus 1. So that one would be convolved by the same thing, so 2 to the n minus 1 times u to the n minus 1. And you get this by just doing a similar thing where you divide by, you multiply and divide by z inverse, so you times, so z minus 1 times z minus 1, and then you'd get it into the form of what corresponds in that table. So yeah, that's the z-transform. That's how you invert the z-transform for the most part. You might also see, your professor might also have talked about how if you have a polynomial in the denominator, so if you have like quadratic, then you can actually do partial fractions again, where you have like a linear term up top too, times like your quadratic. That also works, but I'm not going to get into the details there, just because you can multiply across, and you multiply everything by this denominator, and then solve out for the coefficients a and b using the method of determining coefficients. So you get like a linear system, and then you get a and b. But for the most part, I don't think that you'll see this on your exam. So that's just trying to be annoying. And usually you can factor that. You probably won't get a problem where it's easier to do it. Like this. It's probably going to be where you're going to factor this into like, you're going to factor it. That's that's always going to be easier than if you're going to do this outright. That's 2 or something. I don't know. Whatever comes out to this quadratic, you should try to factor it. Go ahead and turn on the light. It's pretty dark in here. I don't live in a cave yet. But yeah, here we go. So we have. So we can invert z-transform. Great. We learned how to do that. But now what do we do at this point? So let me try and define a more real-world type problem. So let's say that you're looking through a bunch of code and you see the following function. So y of n is equal to x of n minus 2 plus x of n minus 4. Yeah, so what do you do here? I'm going to say 1/2. 1/2 x minus 4. So you see this and you go, well, what does this mean? What does this do? There's no comments, because of course there's no comments. So what are we gonna do about this? We're going to analyze it as a system. So like I said before, you can analyze any input-output relation via the z-transform. Input-output relation in the discrete domain via the z-transform. So I'm going to go ahead and turn this into a system. So you do this by taking the z-transform on both sides. Y of n. So z-transform of that one equals to the z-transform of x n minus 2 plus 1/2 x n minus 4. Okay, great. So we have that. And then we apply linearity again. So let me just go ahead and write this in terms of z. So this is yz, easy. And we get x of, so remember the time shift property, so we're going to multiply by z to the negative 2, xz. Remember linearity, we can always just take out coefficients. You can always take out additions. So we also get a time shift in our time domain signal again, xz. And now, so we want to get it into, so what we want is to get it into the form of just a single system, just a single system transfer function, h. And we'll get this by factoring our z-domain signal, so our output over our input, xz. And we can do that pretty easily by just taking out, remember these are just coefficients that multiply xz, these are both the same, so we can take it out. We can go z minus 2 plus 1/2 z minus 4, and we get xz. Great. So we got the following relation. We got this one, xz is equal to yz. This one is equal to yz. Is equal to y. Okay, great. So we got that. And now if we divide by x on both sides, then we can get yz. So we'll get yz over xz is equal to z minus 2 plus 1 half z to the minus 4. Okay, so great. And remember that this is our definition of h. That's our output over our input. So that's our system. That's our system that we can get from our z domain. So, right. So how can we go about analyzing this further? We would ideally want to be looking at the spectrum. So, but that's kind of out of the scope here. So this is good enough for our purposes. This is, if you're asked to derive the system from an input-output relation here, a difference equation, then this is how you would do it. Okay, so that's great. That's great. So let's go ahead and do another one. So let's say that we are given like this one. So y n minus 1 minus, let's do another one for posterity's sake. So yn is equal to x of n plus 4. Yeah, great. So we can get this. So we can get this. So we get y z z minus 1, because we have a time shift, minus yz is equal to xz plus 4. So now let's go ahead and factor it out. So we get yz over, so let's get yz okay, so yz, let me just go ahead and write everything out, so I didn't resolve this ahead of time. So let's go yz minus 1 times yz is equal to xz plus 4. Then we probably do this, so we get algebra. Just doing some algebra. xz over plus 4 yz. Then you can probably multiply by, let's go ahead and try and subtract that 4 over yz term. 4 minus 4 over yz. Common denominator, okay. xz over yz. Then let's get a common denominator here, so we get yz times yz times z minus 1 minus 4. Okay. Let's go ahead and bring this to the other side. We get xz which again, kind of where we started. So, okay, well, let's see. I made up this number, this equation on the spot. I don't think that you'll be given one where you'll just have a constant added. But let's say xn minus 3. So let me go, so xz, so 4 z to the minus 3. So I'm changing the problem a bit. So we get this. Let's go ahead and get a valid relation. Because like if we don't have linearity, then we won't be able to do this z transform type thing. We still got to make sure our system is LTI, and I'm pretty sure what I wrote it didn't satisfy one of the properties. So let's go ahead and write out. So we get 1 plus 4 t minus 3 xc, and we get h is equal to. So we take this one and then we divide. So we get this one over here on the left. We take it over, we bring it over, so we get 1 plus 4 z minus 3 over z minus 1 minus 1. So that's our h. So that's our system. And again, you could probably take the z inverse and then probably invert the z transform, and then you'd probably get a time domain signal that corresponds to that. How about I just go ahead and do one where it's simple so that we can see what I mean by that? Because we can represent any system as a convolution in the time domain. So let me go ahead and try and illustrate that. So if we have, so let's say we're given the difference equation here. You're looking through your code again and you find this one, yn minus yn minus 1 is equal to xn. So what do we do here? So let's go y or z, and once you do a lot of these, you can kind of start seeing the pattern pretty quickly. xc, and you can get the following. So we get h z is equal to, so if we just divide by this term on both sides, then we'll get 1 over 1 minus z to the minus 1. And now, this is our system for this difference equation. So now, what do we do now? What do we do? So we need to, so let's say that you're told to, find impulse response. So let's say that we were told that from this one. What would we do? So we have our system function, we have our transfer function, so we can take the inverse z transform, and then we'll get our impulse response in the time domain. So this is the z inverse of 1 over 1 minus z to the minus 1. So we notice that this one looks kind of similar to what we've been doing earlier, but we're missing something. So we need to have specified something more about the signal, because remember, there's multiple signals that can have the same inverse z transform. So they can have the same z transform, but they'll be different in the time domain. And this is specified by the ROC. So we need something that specifies our ROC. So we're asking, what is our region of convergence? And you'll notice in the problem, they actually said that you want the causal impulse response from this z transform. So how do we get that? So notice that we have the poles here. So let's try and get the poles of this. Let's try and plot that. Let's go ahead and plot the zeros and poles of this transfer function so that we can really be sure. So notice that this one will go to 0 when z is equal to 1. So we get a pole at z equals to 1. So what is our region of convergence if we want a causal impulse response? So if it's causal, then remember that we want to be taking the outside of some circle. And so this would specify that we need to have a circle outside of 1. So everything outside of 1. That's our region of convergence. Great. So now that we know the ROC, so great, yay, we have the region of convergence. So now, what is the impulse response here that we get from our inverse Z transform right over here? That's going to be just a unit step function. So, what do we learn here? So we get h of n is equal to the unit step function. So, what does this mean? What does this mean? So, remember that we were given this one at first. We were given this discrete time difference equation, and we get some impulse response. We get some impulse response, and while we do that, what do we do with a system's impulse response to apply it to a signal? We convolve it. So if we have some signal xn, and we convolve it with hn, this would give us the same thing that we would get as if we applied this process over all n. And that's pretty huge, because depending on your problem, this will either be easier or this one could be easier. It really depends on what you're working in. So it's good to have both representations available. So let's see. Let's go ahead and try and do another one. So let's go ahead and say, let's say you were designing like a circuit or something. So your boss says, make me a filter. Make me a filter. And you look up filters online. Make me a low pass filter. And you find the equation xz is equal to 1 over 1 minus, like, say, like 1/4 z inverse. So what do we do here? What do we do? So let's say you were told to implement this filter. Oh, I guess it's nighttime now. Okay. So we want to implement this filter in software. We want to implement it as a digital filter. Digital. So how do we do that? So a lot of times, unless you have special libraries for actually working with these Z transforms themselves, like say you're working with like a symbolic math library, then you could probably just apply it directly by just multiplying by whatever you're. Let me just write this as h, because this is our system. This is a filter. This is something that filters our signal. So if we just have our Z transform of some input, we just go ahead and multiply that across, like if we had the right libraries. But let's say that we don't have that. So how do we implement this filter? How do we do that? How do we do that? I'll lose my job otherwise. Okay. So let's go ahead and try and derive an input-output relation. That sounds like a smart idea, because we can usually run through an input-output relation, so like y, z. In the time domain, we can do that by just a loop. Sounds like something that's pretty reasonable. So let's go ahead and try and get what, so we just need, what we want is a summation of yn delayed by like a series of k values. And then we want that to be, have like a series of x n minus k, n minus l. So we just want a series of delayed input terms too. Yeah, copies of our input. So that's what we want. That's what we want here. Red. Want. Okay, so that's actually pretty easy to accomplish here. So remember that h of z, we can always, if we have any arbitrary impulse response, or if we have any arbitrary system function, our transfer function, we can always factor it into a output over an input. Just because we're restricting the functions that we're working with to rational ones. So let's go ahead and multiply across and see what we get. So we got this one. Let me go ahead and erase this. We're not working with h anymore. We're concerned with outputs and inputs. What do we get? So let me go ahead and do some algebra, and let's go ahead and multiply by xz on that side. So 1 minus 1/4 z inverse yz. And then let's multiply across here. And then we get xz. So if we multiply across, and then we distribute, we get yz minus 1/4 z inverse times yz. And now, we can actually invert the z transform here. Because if we use our properties again, then we can go ahead and derive a time domain signal. We can define a time domain relation. So let me just go ahead and invert. So now let's invert. So z inverse of this one, this whole thing, this equality. So what do we get? We get x of, so let me just go ahead and write out everything. Let me just not try and cut any corners. Let's not do that. So it's z inverse of all of these. yz. Remember, we can apply linearity so that we can take out coefficient. Z inverse of z minus 1 times yz. Okay? Great. So, what do we do now? We can go ahead and z inverse. So, this is our time domain signal. So, just the z inverse, or the inverse z transform of xz is going to be xn. It's just the same signal because we didn't really do anything to it. So, we get the same thing for y. No, it's an n. So we're in the time domain again. And then minus 1/4 times whatever the z inverse of the inverse z transform of this yz times z inverse. So what is that? Remember that the time delay property. Remember the time delay property. Whatever's in the exponent here, you can just bring it out into the domain there by just taking that exponent and just dragging it over. That's the idea. And great, so we got this input-output relation. We get this difference equation. And now you can, so since we're implementing this as a digital filter, we're implementing that in the time domain so that we can just like write like a for loop and then go like, alright, so we get xn is equal to yn, and then minus that for n. And that's how you'd write it out, and that would be a digital filter. Most of the time, a lot of times that's how you can do it for that application. I'm kind of trying to speak from a bit more of experience, but let's see. So that's the Z transform. We covered that, I would believe, pretty well. So we also need to talk a bit about sampling. So I'm kind of going in reverse order of the presentation that I just gave. So let's go ahead and talk about sampling. So if we have a signal, let's say we have a continuous time signal, xa of t. And we want, so let's say you're told, like, we have a microphone that records an electrical signal. We get an electrical signal, which is in the continuous time. So xa of t. And let's say that our original signal is just a cosine. So this output from our microphone is just going to be a cosine. So let's say this cosine of t. Cosine of 300 t. Great, because we want this cosine has a certain frequency. So let's go ahead and try and sample. Let's sample this at, so we have a microphone that creates an electrical signal, and we need to put this into a computer because that's how we work with a lot of our signals. We're in the age of computers. Computers are good. So let's go ahead and try and sample it. So let's say our sampling rate is 16,000. Yeah, so it's 16,000. Wait, no. Our sampling frequency, not t. T is 1 over fs. Our sampling frequency is 1600 hertz. And remember how we get t? We go 1 over fs, and we get 1 over 16k seconds. So, what do we do? Alright, so sampling. So xn. So if we remember that one equation that I showed y'all, go back to it. So remember that if we have a time domain signal, then we can apply this one right here, and we'll get our sampled signal. So let's go ahead and do that. So xn. So let me go back to OneNote, back to writing, back to my handwriting. So we get xa. So we get a sampled analog signal at a series of points corresponding to our sampling rate. And since we have that, since we have a number for that, let's go ahead and just plug that in. So n over 1600. So now, what was xa? It was cosine. So cosine of 300, so what's inside here becomes t, so 300 n over 16k. So, right, so that's our discrete signal. This is what we would get. Now there's more to talk about here. Specifically, we don't usually use this. We use what's called a normalized frequency, where we get this fraction into its lowest terms. We take out a 2 pi term so that we can make sure it's periodic. But this would be a sample signal. And I think this works for whatever we need in this class. So let's do another one. We need to talk about the sampling theorem. Okay, so I'm trying to think right now. So let's say we're given okay, so let's throw in modulation here too, because I think that I can incorporate that here. So let's say we're given a continuous time signal here. So this is our x. This is x. Yeah, let's say this is x omega. And we're trying to get a sampling rate after we kind of mess with this, because we have this in the frequency domain. We have this frequency domain signal, and we can still kind of process things in the time domain, the continuous time domain. This analog filters, that's continuous time stuff. There's certain things that we can do, but I'm specifically interested in what happens whenever we multiply this x omega, times, so let's say you're told that yn, so let's say you're given the following diagram. So xt, so we're in the time domain, we're in the continuous time domain right now, because we're talking about sampling. And so if you bring this and then we multiply it by some cosine omega naught t. So we multiply it. This is the multiplication symbol. And then this is y. Yt. Okay? Great. So that's our output y. And then we want to sample. So sample. And this will give us, let's say, h of n. Let's define some discrete time signal. That's what we want. So we want to multiply, so this modulated signal, or x, and we want to sample that modulated signal. And I'm going to ask, like, what fs, what do we want for fs? So, because this one has fs. Yeah, what is our sampling frequency? So, remember, so like I was talking about, we're modulating our original input by this cosine. That's usually what we say when we're multiplying two signals together, or modulating one by the other. So, this one, the x of t. So if we remember, if we multiply two signals in time domain, we get a corresponding relation in the frequency domain. And yeah, notice that these are both time domain signals. They have t's. Yeah, this is omega 0. This is just some number. Okay, so remember that this is going to have the relation x omega convolved with cosine. So whatever the Fourier transform is of our cosine. Cosine omega naught t. So what was the Fourier transform of a cosine? It's going to be two delta functions. So this is going to be two deltas. So let me just write that out. Convolved with two deltas, which are both centered at omega naught and negative omega naught. So delta omega minus omega 0 plus delta omega minus, no, plus omega 0. Cool. So, and remember what we were talking about earlier, that if we convolve by a delta function, then we'll just get a copy of our function that we're convolving with centered at that delta, and wherever that delta is defined. So we get, so let me just go ahead and distribute this convolution operation, because you can do that. So convolve. Yeah, convolution satisfies the distributive property. So plus, so that one, plus x omega, convolved with this other delta, omega plus. Remember, convolution is a lot like multiplication. We have a lot of the same properties. So we can get x omega minus omega 0. So we get another one, x omega plus omega 0, because this delta is centered at omega 0. So notice that if we multiply by a cosine, we get two different copies of our original spectrum. So let's go ahead and try and draw this. So this, if our original spectrum was that triangle, then we get these two. We get these two. And this is omega 0, negative omega 0, so this one's omega 0. Okay, great. So that's what we get in our output. So this is y. So this is a spectrum of y. Y omega. Because this one is equal to y. Yt, yeah. So this is y omega. So now, notice, if we were to sample at, say, twice of this frequency, so let me say that this is b. So it has the bandwidth of b. That's the maximum frequency. So if we were to sample at twice this bandwidth, then notice that we'd have something that's going to have a lot of aliasing, because the maximum frequency here is not B, it's 2 plus, or it's omega plus B. And also we get the same thing over here, so negative omega minus B. This is our max frequency now. And we need to have our sampling frequency reflect that, because we're not sampling our original signal, we're sampling a modulated version of our sample. We're sampling a modulated version of our input. So, what do we do now? So, if we remember the Nyquist criterion, so we need to have that, so we need Fs. Remember, we're trying to find Fs. So, we need Fs is greater than or equal to 2 times Fmax, so the maximum frequency. So Fmax is actually here. So this is 2 times F omega plus B. And I'm going to divide by a 2 pi here, just because omega is equal to 2 pi F. So if we want F, then we divide by 2 pi. Right. So dividing by 2 pi is because we want F's. So now we get following, so this one's equal to, no wait, there's no 2. 2 is cancelled. We cancelled U2. So we got that. So actually, we got our answer. So we need our sampling frequency. So Fs is, it needs to be greater than or equal to this, whatever this value is. So if we were given like a bandwidth of say 4, then if we were given a bandwidth of 4, then all of these things would, then we get 4 here. Oh wait, I dropped a naught. Yeah, omega naught plus B. Yeah, have it over here, because that was the original frequency of our cosine. So if we have omega naught plus 4 now, our bandwidth, divided by pi, that should be our sampling frequency. We can choose any number here as long as it's over that value. And a lot of times we'll choose a number that's greater than this, because in many applications it's important to be oversampling rather than just right. But like some might argue it produces better quality signals or whatever. But for our purposes, all that matters is that it's greater than or equal to. So if we had it exactly equal to our time domain signal, if we had our sampling frequency exactly equal to this omega naught plus 4 over pi, then we would still be able to reconstruct our time domain signal by having the filter defined by this one. That's all we need. We would get the exact same thing. It's not like you would get a different signal from what you got out if you have this criteria. So great. That's 2 birds with 1 stone, kind of, I guess. I think that's a good illustration of Nyquist, the Nyquist rate, and also modulation, because that's also a topic that's talked about in some of the sections. And yeah, I think that's pretty good. But let's see. So we have about 20 minutes left or so. So I mean, if y'all have any other questions that y'all would like to ask, go ahead and shoot. But let's see. I'm basically just going to have one more example where I cover a bit on the Laplace transform, and I'm just basically going to derive an input-output a differential equation from a impulse response, or vice versa. And you'll see that it's a very similar process to that of the original Z transform stuff we were doing earlier. But yeah, if there's no questions, then I'll go ahead and do this. I'll go ahead and go, well, this is X.
Dropped one in the whiteboard.
Oh, what's that? Oh. Okay, let me go ahead and see that. Yeah, we got a question coming in. Okay, so got that. So let me go ahead and try it and just save that. Let's see. Let me try and point OBS to Discord. Okay, so we have this question. So let me go ahead and bring this over. OneNote so I can start copying stuff. But let's see. So we have this. Alright, so we have a discrete time signal here. So this is xn is equal to negative alpha over 4 times unit step n over 2. Oh wait, that's a 2 times u of n. And what we're asked is to compute the Z transform. And under what condition on A does our Fourier transform converge? Okay, so we have two steps. A, so Z transform. I'm pretty sure in MATLAB it's called Z trans. That would be like the function you'd use. But and then when does, so x omega, when does that work? Okay, so let's see, what kind of signal do we have here? So remember those classifications that we were talking about earlier. Let me just go ahead and put it back on OneNote. I have all of the information from that. Okay, so what do we have right here? This is a non-causal signal. Just because if we were to plot out the values of this one, then we get something that exists on both sides. And that's because we have this absolute value in our exponent. So like if we have, so we have this non-causal signal, but we're multiplying it by a unit step function. So actually, my mistake, this is actually going to be a causal signal. Great. So that makes it even easier for us. Yeah, so if we hit it with the unit step, then we get, yeah, something on the right side. These aren't the actual values, but just as an example. Okay, so let's go ahead and try and take the Z transform here. So let's see. So if we remember the definition of the Z transform, then it's defined as like this summation. So if we get summation of this negative alpha over 4 n over 2 u of n times z to the minus k. Oh yeah, no wait. Why did I say k? This was n. And this is defined for n from negative infinity to infinity. Okay, so let's see. What do we do now? So the first step that you would do to take care of, so the first step would be to take care of any of these unit step functions that you have. Apply linearity or whatever to make sure that you have it in the form where you're just multiplying something times a unit step. So that you can do this. We get 0 and then infinity. Because this unit step function, remember that it's 0 for everything outside of everything less than 0. So none of these terms that exist below n is equal to 0 are going to matter. So if we have that, so we can cut off our summation and get rid of our unit step function. So we got n over 2 now. Cool. Wait, let me go. look back at that problem. What's that? That a floor or something? No. Okay. So it's just an absolute value. So I'm going to go ahead and assume that this is that n is going to only exist for what's it called, even numbers, just because it doesn't really make sense to talk about x to the 1.5. Yeah, this one doesn't exist because we're working in the integers. So let's go ahead and rewrite this with an m. So m is equal to n over 2. Let's apply substitution. So we get that, so summation m is equal to 0 to infinity, and then we get minus alpha over 4 times absolute value of m, and then we get zn. So minus 2 to the n, zn. Okay, great. So, and notice that this m value is going to be positive for all m greater than 0. So we can go ahead and just take out the absolute value sign. So now, let's go ahead and see what we got. So let's see. Okay. So we get the sum. Let's go ahead and try and bring in this term into this z. So we can do alpha times z, the m, because we can always kind of factor out, remember that z to the minus 2m, you can always take out one of the exponents. So z minus 2 to the power m. Oh, let's go ahead and bring that negative sign too, just for reasons you'll see later. But we got z over 2 over 4. And we can do that. And these two should be equivalent. Alright, so yeah, what do we do now? So, one thing that I didn't really go over, but it is kind of important, is how we actually, so why do we define our region of convergence like we do? It's because we want to be able to use the geometric series formula. So if we have, so remember that if we have, so this is a whole other thing that we should have covered. So I'm going to write it in blue. So if we have just some series of, say like k is equal to 0 to infinity. So the summation of some number r to n, then this summation will come out to a certain value. This will be 1 minus r. And this is as long as r is less than 1. Because if we have it like equal to 1, then like we get a bunch of, yeah, if we have it equal to 1, then this sum won't converge. We'll get like just an infinite series of 1s. And that's not something that we want. But if it's less than 1, then this, multiplying it by successive values of n, then this signal will decay. Like this r will decay, and we'll get a convergent series. So this is the geometric series. So that's something that we should have covered. But that's why we talk about the region of convergence. Because when we're deriving these z transforms, we're working under the assumption that the z transform converges. Yeah, we're assuming that our series converges. So everything's defined as a series. So if we apply that formula, that 1 over 1 minus r, then we get this one. We're assuming that that exists. And under what condition did that converge? So if r was less than 1, so our new r, so the r that we have in our series is negative alpha z minus 2 over r over 4. So that's our 1. That's our r. Oh, actually, wait. Hold on. Ah, wait, no, that works. Okay, so if we have that, then we got, so probably that one, because it was supposed to be absolute value of r. R is less than 1. Okay, so we got alpha z minus 2 less than 4. So we get z minus 2 is less than, so the magnitude of z minus 2 is less than alpha. Oh, 4 over alpha. And then we can, yeah, so let's multiply. So this, let me rewrite this. So z minus 2. And let's go 4 over alpha. And yeah, this one's equal to just, we can bring down that absolute value, b squared. So let's go ahead and go. So we got 4 over alpha is times z squared times 1. So that's all greater than 1. And then we got, so let me just bring everything over. So alpha over 4 is less than z squared. And let's go ahead and take the square root on both sides. So alpha over 4 is less than z. Right, so that's our absolute value. So notice that this looks pretty familiar. This is our region of convergence for this series. And this one would be our z transform. This is kind of interesting. So let's kind of try and go back to what we were asked. So we need the z transform, as well as what values that the Fourier transform will converge. Okay, so the Fourier transform is the z transform where z is evaluated, so z is equal to e, so it's evaluated over the unit circle for omega, for all omega. And when will the Fourier transform converge is really asking about when will our z transform converge a lot of times. So if we have a convergent z transform, we just need to make sure that, our, as long as we have our region of convergence include the unit circle, we need to make sure that this includes the unit circle. So whatever it is, no matter if it's, so I'm going to draw the, let me go ahead and do that again. Let me draw the unit circle. So I wasn't really sure what they covered in each section of this course. I have a rough idea, but if we have the z transform and then we have it include the unit circle, then our system is what we call stable. So if we have a causal one where we have a pole right here and then you take everything outside of that pole, then that would be a causal stable system. If we have a pole way out here and we want the anti-causal z transform, so this would be everything in here, so this would be a anti-causal stable system because it includes this unit circle. Notice that both of those that I drew include the unit circle. That's what we're concerned about. So if we have our Fourier transform converge, then we need to make sure that this condition is, this one will include the unit circle. But let's go ahead and try and draw out what this means. So let's see, so alpha over 4 is some number. So let's put it, let's say here, alpha over 4. And if we're looking at z, the magnitude, such the magnitude is z is greater than alpha over 4, then we're trying to take everything outside here. And since it doesn't include the unit circle, then so this is our region of convergence that we defined here. And if it doesn't include our unit circle, then our Fourier transform won't converge. So if we have it way out here, then we won't have a Fourier transform. But let's say if we have our alpha over 4, so because we can choose alpha, right? Alpha over 4. Right, so what about if we had here? So remember that we're taking everything outside of that. So notice that this is including the unit circle here. So our Fourier transform will converge. This is a causal region of convergence. We need a causal stable system in order for our Fourier transform to converge. So that's essentially what we got. So we need that alpha over 4. Yeah, because, okay, so let me go ahead and just write this explicitly. So we have alpha over 4 is over here. It's less than 1, because this is the unit circle. Everything is magnitude 1 on the unit circle. So what we actually need is for alpha over 4 to be less than 1. So what does that mean? So let me go ahead and do some algebra. So alpha square root of alpha over 4 is less than 2. Yeah, because if you just take out that 4, we can get a 2. Yeah, so we get square root of alpha is less than 4, or less than 2. And then we got alpha is less than 4. Okay, so that's our condition. So when do we get a Fourier transform? When alpha is less than 4. When we get a z transform, what was our z transform? It's this. Let me just go ahead and write it a bit cleaner. So this is 1 minus, so this is plus because we have a plus sign. Alpha over 4 plus alpha over 4 z to the negative 2. And that's your system h of z. Or whatever. Oh wait, so we're asking for x of z. That's our name for it. X, not h. And yeah, that's it. That's our signal. That's our system function, our transfer function, our z transform. So that's the idea. So we got both of those down. And right, so it seems like we're about at 9 o'clock. So if anyone has any questions that they'd like answered, then go ahead and just shoot them in. I can take a second to answer them. But yeah, anyway, good luck on y'all's exams. If y'all liked this course or wanted to, understand a bit more, because I know that this course is a lot on your first run, because there's a lot that is kind of just blown by you, like, okay, this is something you gotta accept. But I think this is a subject that comes with time, and something that you'll learn more as you take more courses. So one that I really recommend for you to take is DSP, Digital Signal Processing. I think it's like EE 4360 here. And that's a really good course. You'll be talking about how do we implement these. So I kind of glossed over, how do we implement these digital filters in real systems? That's the main topic of the course. How does everything really connect here between like the Z transform stuff and the spectrum? I kind of glossed over that. So if you want to learn more, that's a thing. If you want to talk more about modulation, take communication systems. That's EE 3350. It used to be required, but it is now an elective. But anyway, you'll talk about basically how do we communicate between different types of devices, and what different schemes that we did. So remember that modulation thing that we were talking about earlier? Yeah, this one. Yeah, so this is amplitude modulation. This is AM. Yeah, this thing where we multiply by cosine. Yeah, I don't know if y'all are familiar with AM radio, but yeah, that's the idea behind that. We multiply by a cosine, and then we get a signal up in high frequencies that we can go back down into the low frequencies once it gets back to your phone or your computer, whatever's receiving your signal. And that's cool because, I mean, we kind of overcome this limitation where we need to be, sitting next to each other to communicate something. We can now send things over the air because due to like physics and stuff, it's good to have things up in the high frequencies. It's easier to communicate those over the electromagnetic spectrum than it is to communicate a baseband signal. But yeah, I think those are the two courses that I learned a lot about these topics from. Yeah, but yeah, if you have any other questions, go ahead and DM me on Discord. I'm free, or just post it in the tutoring chat. I also look at that. No one really comes for signals very often. Maybe the professors are pretty good this semester. So but if y'all have any other questions, go ahead and just hit me up. Also, if you like this course and you'd like to try learning more by like trying to, I think that one of the best ways to learn is by teaching it, which is why I'm up here today. And one way to do that is by tutoring. So if you'd be interested in that, then yeah, you can go ahead and hit me up or Marie in the tutoring chat in the IEEE Discord. Yeah, that would be great. We need more signals tutors. Usually there's a lot more questions that go unanswered for this section just because there's few tutors for it. Also, as a side note, I'll be I guess I'll be retiring from this post, say, next semester. That's when I graduate. So if anyone wants to start taking over, if anyone wants to be a head tutor, it's a leadership position. You'll get valuable experience doing public speaking. You'll get a hell of a lot of practice on the signals material, which will come up time and time again in like a lot of your courses. So yeah, there's a lot of benefits to doing that. And if you think you'd be interested, shoot me a message. Or Marie, she's the tutoring director. But yeah, we'll be looking for a replacement soon. But yeah, good luck on your exams tomorrow, y'all. I know this course is hard. You'll deserve like a pat on the back like whenever you get done. So yeah, almost there. Good luck, stay safe. I think that's it. See y'all.